This is the second section from chapter 4 on recurrence relations, and here we're going to be looking at solving first order recurrence relations. Now we know that a recurrence relation, I'll just call it RR, gives you the next term from previous terms. Okay, next term from previous term or terms. Now, that's not always useful. We often want to find a particular term in a recurrence relation, a bit like the nth term rule. We call this the solution or the closed form of a recurrence relation. Okay, so solution or closed form of a recurrence relation R again gives us any term in a recurrence relation sequence by using n. So it's not reliant on finding the previous term. So when we find this solution or closed form, it's going to be un equals some sort of function of n. It's not reliant on un minus 1 or un minus 2 and so on. It will give us any term in a recurrence relation sequence. Now, a first order recurrence relation will be of this form. So un equals something times by the previous term plus some sort of function of n. Now, depending on the form of this, what the values of a and g of n are, will tell us what approach we're going to take to solve it. So first of all, let's look at recurrence relations where this bit g of n is equal to 0, so there's basically nothing here. So g of n equals 0, and we give these recurrence relations a special name. We call them homogeneous. So homogeneous. So a homogeneous first order recurrence relation will be something like un equals something times un minus 1. There won't be this g of n part here. So g of n will be equal to 0. So basically what we're going to have is a recurrence relation that looks like this. Un equals a times un minus 1. And what we're interested in is what the solutions are, or the solution is, for this homogeneous first order recurrence relation. Now, if we have a recurrence relation where u0 is given, then the solution will be of this form. Un equals u0 times by a to the power n. Okay, and a is this number here. If, however, we get a question where u1 is given, then the solution will be un equals u1 times by a to the power n minus 1. So this is how we solve these homogeneous first order recurrence relations. So now let's look at where we've got recurrence relations where g of n is not equal to 0. So there's some sort of function of n at the end. So it might, I don't know, say something like 5 to the power n, 2 to the power n, 2n minus 3. Okay, so that will be tucked in on the end there. This we call non-homogeneous. So this would be a non-homogeneous first order recurrence relation. Now, with these non-homogeneous first order recurrence relation, these can be split into two types. We can look at types where the value of a here is equal to 1 and the value of a here is not equal to 1. So we'll just write down here a equal to 1 and a not equal to 1. And we've got a slightly different approach for each. So let's have a look at the type where a equals 1. So we're going to have a recurrence relation that looks like this. Un equals, and since a equals 1, we're just going to have un minus 1 plus this part that's here, this g of n. Now the solution for this one, or these types, will again depend on whether u0 or u1 is given. So if u0 is given, then the solution is going to be un equals u0 plus the sum of g of r from r equals 1 to n. Now, what does that mean? Well, basically, we write this function here in terms of r. So to get from here to here, we basically replace n with r. We write the function in terms of r, and we're going to find the sum of that function from 1 to n. If, however, u1 is given, then the general solution becomes un equals u1 plus the sum of g of r, but from r equals 2 to n. And again, just like before, we'll find, or whatever g of n is, replace n with r, and we're going to find the sum of it from r equals 2 to n. So the last type of non-homogeneous first order recurrence relations are going to be of the type where a is not equal to 1. So this might be a number like 2, 3, 4, 5, that type of thing. So the form of that type of recurrence relation is going to be un equals a un minus 1 plus gn. Now, the general solution to this type of question, and we'll talk about the particular solution in a moment, is made up of two parts. The general solution is made up of the complementary function plus the particular solution. Now you'll recognize this from core 2, where you're solving first order or second order differential equations. So a complementary function plus a particular solution, it's made up of those two parts. So how do we find those two parts? Well, the complementary function will be the general solution to what we call the associated homogeneous recurrence relation. In other words, the general solution to this part. And how do we find a general solution to that part? Well, it's what we do over here, but it's going to be slightly different because we're not going to have u0 or u1. We're going to have an arbitrary constant c. So the complementary function is always going to be of this form: c times by a to the power n, where c is an arbitrary constant, and a will be the value of a here. Okay, so I'll just write down what this actually is and why we do this. So this is the general solution, I'll just put general sol, to the associated homogeneous, that's basically this part here. So this minus the g of n, take away the g of n part, the associated homogeneous recurrence relation, and I'll just put r. So that deals with the complementary function. So the complementary function will always be of this form. We also need the particular solution. This is going to form the other part of our general solution. Now for the particular solution, I'll do it here. We need to look at the form of g of n, and it all depends on the form of g of n. Whatever the form of g of n is will tell us what the form of the particular solution is going to be. Okay, so you'll see there's a table here now. So this table will tell us what form the particular solution will take depending on the form of g of n, so the form of this part here. So if g of n is just a constant, the particular solution will be in the form lambda. If g of n is in the form of constant times n plus q, then it'll be lambda n plus mu, and so on. Yeah. Now this table only works when a is not equal to 1, okay, which is over here. If a is equal to 1, we're better off using this method here. That'll be easier and quicker to use. And also where p, this value of p, is not equal to a. So from this we can then find the particular solution. We add our particular solution to the complementary function, which will be of this form, and then given some sort of initial conditions, we can then find the particular solution. Now, if I use the word particular solution again, it may cause confusion with where we've used particular solution here. So this is also referred to as the final solution. So if I talk about the final solution, this is what I'm referring to, just to avoid confusion between this particular solution and this particular solution here. So our first order recurrence relations, we can have types where there's nothing here, g of n equals 0, it's called homogeneous. These are our solutions to those homogeneous first order recurrence relations. We can have g of n as some sort of function of n, so it's not equal to 0. And then the recurrence relations fall into two types, those where a equals 1, which we can then use this method here to find a solution. And if a is not equal to 1, we need to find the complementary function, which is going to be c times a to the power n plus the particular solution. And we use this table here, compare it with g of n to help us find what the particular solution is. We add together the complementary function and the particular solution to get a general solution, which will have c in it, and use the initial conditions to find the particular solution or the final solution. Okay, so on this question here, it says we need to find a closed form for this sequence. Now, we know that finding a closed form just means finding the solution for this recurrence relation, first order recurrence relation, which basically means the nth term rule, a rule that's going to give us any number in the sequence. So the first thing we need to look at is what form does this recurrence relation take? Well, it's actually of the form un equals a times by un minus 1. The only difference is where we have u, they have a, and where I have my a here, it's got the number 5. And from the first slide, you would have seen that the solution to this type of recurrence relation, seeing that we have been given a0 and not a1, this solution is going to be un equals u0 times by a to the power n. So let's do that. Let's identify what all of these things are. So where we've got u0, it's going to be like a0, so it may be helpful to actually use the letters. So we'll just write down this recurrence relation, which is a homogeneous recurrence relation, because you can see there's no function of n added to this, is of the form, and what I'm going to do, I'm just going to change the letters now, and we change my u's to a's, an equals, I'll use a different letter for a, so let's use the letter b, so that's going to represent my 5, a, and that's n minus 1, where we have a0 equals to 1, and the solution, or the closed form, same thing, solution, closed form, is, again, let's change the letters to a, an equals a0. Now let's have a look what letter goes here. So where I've had an a, I've changed it to b, so it's now going to be b to the power n. So this is going to be fairly straightforward. It's just a matter of quick substitution. So then I will have an equals a0, well that's just 1, times by b, so in this case b is 5, times 5 to the power n. So that just gives me an equals 5 to the power n. So this is the closed form. This is the solution to the recurrence relation. So in other words, I can get any number in the sequence that this recurrence relation generates by using this rule. And I'm going to show you a slightly different way. We're going to do it almost like from scratch. Now this method from scratch, it's got several names. So this is using mathematical induction, so it could be called that. It could also be called recursion. So if you see any of these phrases, they all mean the same thing. Or back substitution. And I'll show you this method. Now, since we have the formula, then we don't need to use this method. But this method here, they're all the same thing: mathematical induction, recursion, back substitution. These are what you would use for proof if you wanted to prove what the result of a closed form is. So we'll start by writing out what the recurrence relation is, which is this. And this recurrence relation basically says you take the previous term, you times it by 5 to get the next term. Okay, so if we sort of carry this process on, then what we're saying is, okay, if I go back a term, so this is why it's called back substitution, then the term before the n minus 1 term, I'd need to multiply that by 5. So it's 5 times the previous term, which is a to the n minus 2. Okay, so how did we get that previous term? Well, we multiplied that previous term by 5. So a to the n equals 5 times 5 times 5 to a n minus 3. So let's see what's going on here. So I'm saying, right, 5 times the previous term gives me the next term. Well, how did I get a to the n minus 1? Well, that was 5 times the previous term. So this is a n minus 1. Okay, how did I get a n minus 1? Well, I did 5 times the previous term. So this bit here is a n minus 2. So this is why it's called back substitution. Now from here, we're not going to sort of keep going, but we want to see what the general pattern is. Now let's say we kept going all the way to a0. So we kept multiplying by 5, and we're going back to the previous term until we get all the way to a0. Now a0 is actually a to the n minus n. Now we're going to work out how many times these 5s get multiplied. Well, if we go back and look at the pattern, n minus 1 was times by 5 once. N minus 2 was times by 5 twice. N minus 3 was times by 5 3 times. So n minus n must be times by n, or times by 5 n times. Now 5 times itself n times is 5 to the power n, times by a to the n minus n, which is a0, and we know a0. So this back substitution goes all the way back to the term that we are given. We're going all the way back to a0, and a0 is 1. Okay, so let's just write down, since a0 equals 1, then by this mathematical induction, recursion, back substitution method, we have an equals 1 times by 5 to the n, which is 5 to the n. So you can see we get the same result as we did before. So we would use this method when a question asks us to prove a closed form. If we just need to find a closed form, we can just use the rules that we have to find the closed forms for different types of first order recurrence relation. So here we have another first order recurrence relation that's of this form: un equals a times u to the n minus 1. So it's a homogeneous first order recurrence relation. And since we have been given a 0, its general solution is going to be un equals u0 times by a to the power n. So again, let me change the letters because we've got a to the n. So we've got a to the n equals, and I'll use my letter B, a to the n minus 1. And so the general solution is going to be a to the n equals a0 times by b to the n. So it's just a matter of substituting it in. So using the lettering that I've got, b is equal to 2, and I have a0 equals 3. So the general solution, or the actual solution, or the closed form, all the same thing, let's write it down. Closed form is going to be a to the n equals a0, which is 3, times by b, which is 2 to the power n. Now, just like the previous one, we could use this mathematical induction, recursion, back substitution method to also find the solution, but we're not asked to prove it, we're just asked to solve it, find it, so we can just use the formula. So we've been asked to solve this recurrence relation. Notice on this one, we've been given a 1, not a 0. So let's write down the form of this recurrence relation. Again, it's homogeneous. There's no function of n at the end. So un equals a times un minus 1. So that's the form of this recurrence relation. Since u1 has been given, the general solution is a, or un equals u1 times by a to the power n minus 1, not a to the power n like the previous one. So this is because a or u1 has been given, not u0. So u1 given. So just like before, I'm going to change the letters so it matches up with the a to the n we've got. So if that were the case, then I would have an equals, I'm going to use letter b, a n minus 1. So the general solution to that solution is going to be an, wanted to write u, so an equals a1 times by b to the power n minus 1. Now here I have b is equal to -3 and a1 equals 6. So my solution is going to be an equals a1, which is 6, times by -3 to the power n minus 1. Now, since 6 is the same as -2 times by -3, we could also write this solution as an equals -2 times by -3, then times by -3 to the power n minus 1. And you can see what we're doing here. We're multiplying this by another 3. So we need to add 1 to this power. So then that becomes to the power n. So then we've got an equals -2 times by -3 to the power n. So that's an equivalent solution. So in this question, we need to find a solution to this recurrence relation where we've been given u0. And if we have a recurrence relation of this form, now this one is non-homogeneous because we've got a function of n here. So this is plus n. So the form of this is un equals un minus 1 plus this function of n. In this case, it's just n. And the solution is un equals, now we've been given u0, so it's going to be u0 plus the sum from r equals 1 to n of g of r. So we have u0 equals 0. We have our function of n, which is this part here, which is just equal to n. So the solution or closed form is going to be un equals u0, which is 0, plus the sum from r equals 1 to n. Now it says g of r, not g of n. So all we do is we write the function in terms of r. So g of r would be r. So for example, if this function here were, I don't know, 2n squared, then we'd write g of r as 2r squared. So we want the sum of r, the sum of g of r. Now from core 1, you'll know that the sum of n, well, let's use r, sum of r from r equals 1 to n is equal to half n times by n plus 1. So that's what we're going to use for this part here. So this equals 0, don't need to write down, so it's just going to be half n times by n plus 1. So there we have our general solution, or closed form, half n, un equals half n times by n plus 1. Okay, this question consists of two parts where we now have these non-homogeneous recurrence relations. So I'll just highlight the part where we've got g of n. So here's g of n for part A, and here's g of n for part B. So let's start with part A first of all. In part A, we're given u0. So that means that the solution is going to be un equals u0 plus the sum from r equals 1 to n g of r. Not sure why I put an extra bracket there, we'll take that out. Now in this question we have g of n is 2n plus 1, so that means that g of r is going to be 2r plus 1. So our general solution, keep saying general solution is going to be u0, which is 7, plus the sum of 2r plus 1 from r equals 1 to n. So using what we've learned from core 1, we know that this is going to be the sum of 2 lots of r from r equals 1 to n plus the sum of 1 from r equals 1 to n. So what we'll now have is un equals 7 plus 2 times, and then the sum of r here from 1 to n is going to be half n times by n plus 1, and then the sum of 1 from 1 to n is just going to be n. You're adding n lots of 1 together, so it's just going to be n. We can simplify that to give a final answer of un equals 7, then the 2.5 will cancel out, so we'll have half, well, just n times by n plus 1 plus n, and I'm guessing we could simplify that. It looks like it's going to be a quadratic, so un equals, now we'll have n squared from multiplying this out, then we'll have n from here plus the other n, so plus 2n, and then plus the 7, so we can write our answer in this form. So part A, this is actually a quadratic sequence. This recurrence relation produces a quadratic sequence, which we can see here. Okay, moving on to part B of this question. Now on this question I'm not given u0, I am given u1. So that's going to change my solution slightly. So here I've got u1 equals 3. So my solution is going to be un equals u1 plus the sum, now not from r equals 1, but from r equals 2 to n. So let's write that down, r equals 2 to n. And that's going to be the sum of r. So, g of r. In this question, g of n, the bit that's added on to, or the bit that I've highlighted in orange there, is 5 to the power n. So that means g of r is 5 to the power r. So to find this closed form, to find the solution, it's going to be un equals u1, which is 3, plus the sum of 5 to the power r from r equals 2 to n. Now, if we looked at this and we thought to ourselves, well, I'm not sure how to find the sum of that. Whenever you're not sure how to find the sum of something, write its terms out and see what it looks like. So, starting with r equals 2, that will give me 5 squared, that goes 25. Then r equals 3, it's going to be 5 cubed. And then r equals 4, 5 to the power 4, and so on. So I need to add together a sequence that looks like this. 5 squared plus 5 cubed plus 5 to the power 4 plus all the way up to 5 to the power n. So this is a geometric series. And what do we need for a geometric series? Well, we need the first term, which is 5 squared, 25. We need the common ratio. Now I can see that each time what I'm doing is timesing by 5. So the common ratio r is 5. And I also need the number of terms, n. And the number of terms is going to be n minus 1. If this went from r equals 1 to n, there would be n terms. But I'm missing the first term. I've got one less term. So n is going to be, the number of terms is n minus 1. And then I can use my sum for n number of terms of a geometric series, which is going to be a times by the common ratio to the power n, however many terms, minus 1, all over r minus 1. Or you can use the form where you just swap these two around, so you've got 1 minus r to the n and 1 minus r. It doesn't matter which way around, you'll get the same solution. I prefer this way around. Okay, so we can now carry on with this. So un equals 3 plus, and then we'll put in our formula for the sum of n terms here. So a is 5 squared times by r, which is 5. The number of terms is n minus 1, minus 1, all over the common ratio 5 minus 1. Okay, now we could leave the answer like this. We're just going to tidy it up a bit. So the first thing to note, I'm actually going to write this over 4, because this is going to be over 4, so maybe I'm going to be able to put them together. So 3 is the same as 12 over 4. Then I'm going to split this fraction up and expand the brackets. Now if I multiply 5 squared by 5 to the power n minus 1, it means I need to add 2 to this power, and n minus 1 plus 2 is going to be n plus 1. So what I'll get when I expand the brackets is 5 to the power n plus 1 minus, and then 5 squared. So let's write that as 25. All of that is over 4. So from there, I've got un equals 12 over 4. Then from this part of the fraction, I'm going to be taking away 25 over 4. And then adding 5 to the power n plus 1 over 4. So giving us a final answer, if we decide to tidy up like this, of negative 13 over 4 plus 5 to the power n plus 1 all over 4, if we decide to write the answer in this form. Okay, so here we need to solve this recurrence relation here. So I can see this is the type where it's non-homogeneous. A is not equal to 1, and I've got a function g of n there. So this is where I need to find the complementary function, add it to the particular solution. This will give me the general solution, and then using the initial conditions, well, initial condition there, u1 equals 3, I can then go from the general solution to the particular solution or final solution. So the first thing that we need to write down is what is the associated homogeneous first order differential equation, and it's just this part here. So the associated homogeneous or homogeneous, maybe that's an alternative pronunciation, the associated homogeneous first order recurrence relation is UN equals 3UN minus 1. And the general solution to this, is of the form C or UN equals C times A to the N. UN equals C times A to the N, and the value of A is 3, so we have UN equals C times 3 to the power N. Let's just correct this here, that's not a subscript, that should be to the power. So our complementary function, therefore, which is the general solution to this homogeneous first order recurrence relation, is, complementary function, not complementary solution. Complementary function is UN equals C times 3 to the power N. So we'll just highlight that so that we don't lose it for later on. That's our complementary function. So the next thing we need to do is to find a particular solution. So we need to look at the form of Gn, okay, and that's of the form 2 or Pn plus Q. So since G of n is in the form a constant P times n plus Q, the particular solution, I'll just put PS, is of the form lambda n plus mu. So our particular solution is going to look like this. UN equals lambda n plus mu. Now we need to find lambda and mu, and the way we're going to do that is to substitute this into the recurrence relation. So subbing into the recurrence relation will give us UN, so UN is lambda n plus mu, equals 3UN minus 1. Now, what's UN minus 1? Well, if UN equals lambda n plus 1, plus mu, UN minus 1 will be lambda, and this n minus 1 instead of n plus mu. So we need 3 lots of that, so it's going to be 3 times by lambda n minus 1 plus mu, and then plus 2n. Now we need to find lambda and mu, so we need to form an equation or equations that's going to help allow us to do that. Now since the constants are lambda and mu and n is the variable, we are going to rearrange this to group together the n terms and the non-n terms, and you'll always do this. So I'll just write down in red here, group together the n terms and the non-n terms. So this is the method we'll use to help us find lambda and mu. We'll always do this. Right, so this just needs a bit of rearranging. So let's group together the n terms. So it just means like multiplying out the brackets here. So I will have 3 lambda n, that's an n term. Then I will also have 2n from multiplying out that bracket. So that's an n term. And there's another n term over here. So if I bring that over, that'll be minus lambda n. Right, now let's group together the non-n terms. So from this bracket here, when I expand that, I will get negative 3 lambda. So negative 3 lambda. So that's a non-n term when I multiply that out. Then I'll get plus 3 mu. That's a non-n term. And then if I move this across, that'll be negative mu. So everything's on one side. Let's now group them together, so I can put the n terms like this. Now when I put them together, I will have 3 lambda n, take away lambda n, so that's just 2 lambda, and then plus 2, so they're all my n terms, and then grouping together the non-n terms, I will get negative 3 lambda, and then putting these together plus 2 mu. So minus 3 lambda plus 2 mu, and all of that equals 0. Now what does that mean? Well, there's no n terms on this side, so this coefficient is 0, and there's no number terms on this side, so this coefficient here is 0. So that gives me two equations. 2 lambda plus 2 equals 0, and from that equation I will get 2 lambda equals negative 2, so that will give me lambda equals negative 1. Then from this part here, that will give me the equation minus 3 lambda, negative 3 lambda plus 2 mu equals 0. Now I've just worked out lambda. Lambda is negative 1. So if I substitute negative 1 into here, that will give me 3 plus 2 mu equals 0. So then I will get 2 mu equals negative 3. So mu will equal negative 3 over 2. So now I have the value of mu and lambda. So I did all of that to find these values here. So the particular solution I can now write down as un equals, now it was lambda n, so that's now minus n because lambda is 1, negative n, plus mu, which is minus 3 over 2. So I will highlight this. This here is my particular solution. Now my general solution is going to be the sum of the complementary function, which is c times 3 to the n. So un equals 3 times c times 3 to the n plus the particular solution. So that's going to be minus n minus 3 over 2. And now I want to find the value of c. And how do I find the value of c? Well, now I substitute in this initial condition, u1 equals 3. Now, if I'm substituting in u1 equals 3, that means I'm also substituting in n equals 1 because this subscript is 1. So what will that give us? That will give us u1, so 3 equals c times by 3 to the power 1 minus 1 minus 3 over 2. So rearranging this, I will get 3c equals, now I've got 3 on this side, so I'm going to add 1 to it to make 4, and then add the 3 over 2 to that to make basically 5.5, which is going to be 11 over 2. 11 over 2. Divide both sides by 3, and that will give us c equals 11 over 6. So we found the value of the arbitrary constant. So our final particular solution, or if we like, our final solution will be un equals, so we now just replace this c with 11 over 6. So I'll have 11 over 6 times by 3 to the power n minus n minus 3 over 2. So there we go. That will be our final answer for this question. Okay, this example here is about a puzzle called Towers of Hanoi. And basically the object of this puzzle is to move all the pegs, or all of these discs, from one peg, so each one of these pegs, from one of these to another. Let's say peg B or peg C. Now there are a few rules. So one of the rules is you can only move one peg at a time. So I could move disc number 1 to peg B or C, so that I can only move one at a time. I can't move 1 and 2 together and plonk them on another peg. A disc can only be moved if it is on the top disc of a pile, so I need to start here with 1, and then if I move 1 to B, then I could move 2, so you can only move the one that's on the top of the pile. A larger disc can never be placed on a smaller one, so I couldn't have, for example, disc 1 here and laying on top of it disc 2 and then disc 3. The largest ones need to be at the bottom. Now when we do this Towers of Hanoi puzzle, you find lots of examples of it online. Normally what it involves is using like a storage peg. So let's say I want to move all of the discs from from peg A to peg C. So what I'd have on peg C is discs 1 at the top, then 2, then 3, then 4, basically like the same way they're piled up but on disc C. So we use like this peg in the middle as like a storage place, and sometimes you might see it referred to as an auxiliary peg. So we're basically using it for storage so that we can get all of the pegs to this one. So basically what I want to do is to end up with 4 at the bottom, 3 above it, then 2 and then 1. Part A says find the minimum number of moves needed to transfer 2 discs from one peg to another. Okay, so let's try and show what this would look like. So the first thing I would have to do is move disc number 1. Let's move it to peg B. Okay, so let me draw what this might look like. So this is my own simple version of the Towers of Hanoi. So I would move disc number 1 to here, like this. So that'll be moving that pile. So you're just left with discs 2, 3 and 4 on there. So let's draw those on. So that's what it would look like after my first move. Now my second move would be to move disc number 2. I can't put it on top of number 1, so I'd have to go onto peg C. So now it's going to look like this, just 3 and 4 left here. So this is my second move. And then my third move will be to move disc number 1 on top of disc number 2. So maybe what I'll do, I'll just put some arrows in here to show the movements of the discs. And this last diagram shows what happens here. So this is my third move. So the minimum number of moves needed to move 2 discs from one peg to another is going to be 3 moves. It cannot be done in any less than that. And you can see that we've used peg B as this auxiliary peg where we're just storing 1 so that we can move 2 and then we'll move 1 on top of it. Okay, now in part B we need to show that 3 discs can be transferred from one peg to another in 7 moves. So I've got a little animation to show this. So here's our starting position here with all 4 pegs on one disc. So there's A, B and C from left to right. So here's move number 1. So this is my first move. So disc number 1 has been moved to peg B. This is move number 2, which is basically the same as the first 2 moves in the previous example or in part A, so the second move. Then here's my third move here. So now I've got 1 and 2 on peg C, so that I've got peg B, this auxiliary peg 3, so that I can now move disc number 3 into that empty position. So this is move number 4, so this is the 4th move. Then this is the fifth move. So you can see what happens on the fifth move is I move this disk over, or disk number 1, back to peg A. Then this is the sixth move. So the reason I moved 1 over was so that I could then move disk number 2 on top of disk number 3. So this is sixth move, I think, from memory. And then lastly here we have the seventh move. So we can see that in 7 moves we can move 3 disks to another peg, and here they've been moved to peg B. So if we were maybe writing this question and we were answering it, rather than draw lots of diagrams, we talk about pegs A, B and C, and maybe do it in a table and show which disks are being moved to which peg, so we could do that in a table. So here are the results in a table. Now what's interesting is that every other move, every second move, seemed to be disk number 1, the small disk. And actually if we carried this on, we'd see that every other move, it's disk 1 that moves. Then every fourth move, starting from here, 1, 2, 3, 4, is disk number 2. And if we carried it on, we'd see every fourth move is disk number 2. And actually if we carried it on, every 8th move would be disk number 3. Every 16th move would be disk number 4. And actually 2 to the power of the disk number gives how many moves there are in between each one. So for example, 2 to the power of 1 is 2, so every second move. 2 to the power of 2, which is 4, so every fourth move. 2 to the power of 3 is 8. We can't see it from this table, but if we carried on, every 8th move would be the third disk. And this might help us when we look to find solutions and work them out. Now part C asks, explain why the minimum number of moves, dn, needed to transfer n disks from one peg to another satisfies this recurrence relation here. Okay, so this diagram that I've drawn here shows stages of what we want to do. So this is what we start with, n number of disks on peg A, and we want to get n number of disks on disk or peg C. So basically I need to get the biggest peg of disk number n, onto peg number C. Now how am I going to do that? Well, to do that I need to move all of these disks above n to peg B here. Now we're told in the question that it takes dn moves to transfer n disks. Now if I'm transferring n minus 1 disks, the minimum number of moves it's going to take is dn minus 1. So it's going to take dn minus 1 moves to move n minus 1 disks onto this peg. Then it's going to take 1 move to move this disk here onto this peg. So I need to add 1 more onto that. Then I need to transfer these n minus 1 lots of pegs on top of disk n. Now we know from the question that's going to take dn minus 1 set of moves. So the minimum number of moves needed to move n number of disks is going to be dn minus 1. Okay, that moves the n minus 1 disks off of the top of disk number n. Then 1 move to move the bottom disk to the empty peg C, and then it's going to take another dn minus 1 moves to move all of these disks on top of n. So we can simplify that and we get dn equals 2 dn minus 1 plus 1. Now since one disk can be moved in 1 move, that means d1 equals 1. So we'll just explain why that is. Since one disk can be moved in one move. So we need to explain the initial condition as well. Okay, we're now on to part D, and part D is asking us to solve this recurrence relation. So the recurrence relation is dn equals 2dn minus 1 plus 1. So the first thing that we want is what is the associated homogeneous recurrence relation. I'll just use RR, and that's going to be dn equals 2dn minus 1. Now the solution to this is dn equals c times by a, and a in this case is 2 to the power n, and this then is the complementary function cf. So we'll just underline that because we're going to need it in a minute. Then we need to look at the g of n part, which is just plus 1. So the particular solution is of the form un equals lambda, because it's just a constant. So from the table, that's where you would see the particular solution dn equals p. Now, since there's no n here to put into this, if un is lambda, then un minus 1 is also equal to lambda. Okay, we now sub this into the recurrence relation, dn equals 2dn minus 1 plus 1. I've just realized I've been using u's, so really I should be using d's. So we'll change those u's there to d rather than u's, so there's no confusion. So the substitution will give us dn, which is lambda, equals 2 dn minus 1, which is 2 lambda, plus 1. So rearranging that, that would give us just lambda equals -1. So now we've got that. The particular solution, I'll just write PS, is dn equals -1. So the general solution is going to be the complementary function plus the particular solution. Complementary function is c times 2 to the n, so we'll write dn equals c times 2 to the n minus 1, okay, because that's the particular solution. Now we can find the value of the arbitrary constant. Since d1 equals 1, we can substitute that in. And if d1 equals 1, that also means that n equals 1, because the little subscript here is 1. So we'll substitute those in, and we will have 1 equals c times 2 to the 1 minus 1. In other words, if we got c times 2 or 2c, and then add 1 to both sides equals 2, so that gives us c equals 1. So since c equals 1, then our particular solution, which I'll call the final solution, is dn equals, then it was c times 2 to the n, c is 1, so it's just 2 to the n minus 1. So there we have our, let's highlight this in orange here, our final solution. Then the last part of this question is part E. Got a little bit of space down here to do part E. I don't think I need a lot of space. Hence, determine the minimum number of moves needed to transfer 15 discs from one peg to another. So the number of moves for 15 discs is just 2 to the power 15 minus 1. 2 to the power 15 is 32,768. We need to minus 1 from that, and that will give us an answer of 3276 7. So I'll just highlight that because there's lots of other working. So there's our final answer for part E. So you should now be able to do exercise 4B on pages 131 to 133. Just a quick recap here because pretty much all of the information is on the first slide. First order recurrence relations will be of this form. When we want to find a solution or a closed form for recurrence relations, it basically gives you any term in the sequence, a bit like an nth term rule. Then if it's homogeneous, in other words, if there's no bit here, g of n equals to 0, this is the way that we find a solution, and the solution will depend on whether you've been given u0 or u1. If there is a function stuck on the end there, in other words, g of n is not equal to 0, we call it non-homogeneous. If a is equal to 1, then this is the most straightforward method to use. Depending on whether you're given u0 or u1, this will give us the solution. And if a is not equal to 1, then we need to find a complementary function, which is going to be un equals c times a to the n plus the particular solution. That will give us a general solution. Then if we substitute in the initial condition, we will then get the final solution.